right, so I'm here with Taiki, and we're going to be live solving the team round from our 12207 test. This is the state championship meet for high schoolers in 2022, particularly April 2022. All right, so I'm going to just put the test up here, and Taiki and I will go through some problems one at a time. I'll create some space for us to work. I will be writing in red, and Taiki is writing in, what color are you writing in, Taiki?
Blue.
All right, cool. So we've got our test set up here, and I'll create some space for us both to work on it. And this is Taiki. Have you seen these problems before? This is the first time I'm seeing the problems as well. So we're going to get a chance to show people what happens when we look at these problems for the very first time, right? How are we going to solve these? What kind of things would we do to figure this all out? All right, so let's take a look at problem number 2. All right, Taiki and I are going to spend a moment reading this one, and then we'll get back to you with our thoughts on how to do it. All right, I'm going to make a little drawing here first. So we have the cities M and A, and it looks like we have 9 stopover points on the way through. So I don't know how best to draw 9 things here, but and it looks like these are all 100 miles apart. Okay, and we are trying to travel from one place to the other, and we're going to meet along. So let's say we meet at a hotel. Boom. All right. And we want the probability that the sum of the squares of the distances from this hotel to each traveler's hometown. So in other words, the distance over here and the distance over here is no greater than 700,000. All right. What do you think, Taiki?
First thing I would do is scale the hundreds down. So like,
nice.
Yeah, instead of 100, it'd be 1, and then 700,000 would cut by 4 zeros, since 100 squared is 10 to the 4.
Okay, so we're dividing by 100 with the linear distance, and so when we square it, we're going to divide by 100 twice. So we get rid of 2 zeros and then another 2 zeros. All right, so we want the sum of the squares of the distances to be no more than 70. Okay, cool. So I guess from here, probably a couple different ways to do it. What would be your first approach?
Just try each possible case. Or rather, maybe I would also try like the middle one first, and then see like as we move further left or right how some of the squares will change.
Yeah, I mean, I'm my initial impression is in the middle, you're going to have one extreme, and if we go to farthest left or right, that'll be the other extreme in terms of what the sum of the squares works out to be. So then we could just plug some numbers in. All right. So what do we get? What do we get if I guess we can use each one of these marks here to indicate what the number is. There are 9 different hotels selected at random, so we're going to have over 9. Let's start filling in, I suppose. Let's pick a numbered hotel and come up with some of the squares of the distances.
Oh, all right. So I would choose the middle one and compute that distance.
Mm-hmm.
So if it's the middle, then
Taiki's going to be working from the middle out. I'll work from the outside in then. So go ahead, Taiki. You can do the middle out. I'll do the outside in. So
middle distance from the middle to each of M and A is 5 and 5, so we get 5 squared plus 5 squared, which equals 50.
And I'll I'll write the same thing on mine. This 82 comes from 1 squared plus 9 squared, or 9 squared plus 1 squared.
Squared plus 6 squared. Oops.
And it looks like I've already got it here, right? Because, well, just let me check my work with you. I mean, this is a team round after all, right? So
Yeah.
if I'm getting a 68 from 8 squared plus 2 squared, then I know that anything in between, right? You're getting, let's see, you're getting a 52, you're getting a 50. 52, of course, is going to show up on both sides. I guess the next one would be what, 49 plus 9, 58. So, so yeah, we're basically getting, we're getting no more than 70 in, what is that, 7 of these 9. So that's going to give us an answer of 7x. So that's one way to do this, of course. You know, I'm thinking there's also another way that that possibly could be used if testing these values weren't you know, weren't feasible for some reason, and that is to say, okay, I've got my M, I've got my A, and these are a distance of. And again, I like this idea that Taiki had about dividing by 100. So these are 10 apart. Pick some random distance x, and of course this is going to be x, and this is going to be 10 minus x. If I want to take the sum of the squares, I get 2x squared minus 20x plus 100, I believe. Becky, did I do that right?
I believe so, yes.
All right. And then that's supposed to be no more than 70. All right. So we want this to be less than or equal to 70. We could just divide everything by 2x and move the 70 over. So x squared minus 10x plus, I believe this is going to be 15 now. Is
50. Wait.
Did I get that right? I subtracted 70 from both sides.
Oh, never mind. Yes.
Okay.
So yes.
And that doesn't factor, of course, but you know, we can, if it factored, we would have seen that 70 show up in our first method. But yeah, what we can do at this point is set this thing equal to 0, quadratic formula it, find out where that, you know, critical point is. It's going to be along here somewhere, and then, you know, we can say, okay, well, any point in between. And so this would have been a way that we could have done the problem if it had been a continuous problem, right? So if rather than we're meeting at one of the hotels along the way, if we chose to meet anywhere at random within this 10-mile stretch, then we actually know what those boundary points are once we solve this quadratic down here, and we could just calculate the distance between those 2 points relative to the overall distance of 10, and we get an answer for that updated version of the problem. Cool. All right, let's move on to the next one.
My first idea is if we want to maximize the score Jill could have gotten, we want to maximize the number of correct answers first, since that will increase the overall score, as opposed to incorrect blank. If Jack gets 3 more correct answers than Jill, then if Jack gets the most possible, which is 30, then Jill has at most 27 correct. So we can work downwards.
So what I hear you saying is that I guess I'll write the names out here. Jack, Jill. So you're saying Jack could get 30 answers and Jill could get 27, and then the scores would be, what would their scores be on this? Then Jack would get 120 for his score. Jill would have, I believe, a
108 at most, so that doesn't work. So we can work.
Okay. Well,
Yeah.
so the idea here is if Jack gets 3 more, yeah, we'll have to work our way down, right? Because if Jack is getting 3 more correct, then just based on the correct answers, we're looking at a 12-point differential. But if Jill's going to get a higher score, what does that mean for us?
That means Jill has to have 13 more based on the other 2 options. Or it's in like,
Yeah, we got 13. We've got 13. We're gonna have to make up somewhere, right?
Yeah.
Jill doesn't get any Jill doesn't get any bonus points, no matter how, for however many she gets, right? The only way to get a differential of 13, right? So we have to cut Jack's score by 13, basically. And the only way to do that is with those penalty points, right? So -1 for an incorrect answer. So that suggests to me that Jack is going to have to get 13 questions wrong. Does that sound about right?
Yeah.
Okay. So what do we put? 17 here. Jill with a 14. Jill's score with 14 correct is going to be 56. Jack's score was 17 correct. If it's all the 17 correct, that's going to be 68. But then we get a 68 minus 13 for the incorrect ones, and that gives us a 55. Now, so one of the things I like to check here is, are we answering the correct question, right? What's the greatest possible score Jill could have received? And of course, Jill's score over here is 56. So the idea is, could Jill get anything higher than a 56? In order to get higher than a 56, she's going to need more than 14 questions right. If she gets more than 14 right, Jack is going to get more than 17 right, which means that Jack cannot miss more than 12. Jack's already got a 12-point advantage by getting 3 more questions, and if we can't knock him down by more than 12, then we can't fit the constraints of the problem. So to me, it sounds like 56 is the greatest possible. All right. Looks pretty good. Let's move on to the next. Okay, Taiki and I are going to take a look at number 4 and figure out what to do. All right. So I love these problems with complex numbers because when I was the age of these students, that was like my favorite thing in the world. Complex numbers. Everything was, anytime I had a chance to figure something out with complex numbers or discover something about complex numbers, I was all about that. So so what are you seeing in this so far, Taiki?
Seeing well, if it's a real number, the product and the sum, then I'm thinking like the argument in the complex plane, the angle formed from real angle or real axis to the complex number has to be 0 or pi.
The sum of the angles have to be 0 or pi, right?
Their sum is a real number, then the angle that the sum forms with the real axis should be 0 pi.
Okay. I think you might be doing a couple things at once. So okay, yeah, that's why I'm not keeping up with you. Sorry. So let's start with the product thing, all right? Because we want to make sure people know how we're getting this. If the product is a real number, what does that tell you about the two?
Tells us that the angles of Z1 and Z2 must add to multiple of pi or 180 degrees.
Right. Okay. Yeah, I was initially thinking one had to be a constant multiple of the conjugate of the other, but it doesn't have to be that way, right? It could be they could be heading off in opposite directions relative to the y-axis instead of the x-axis. Okay, so we know that their angles are going to add up to a multiple of pi. Good, let's keep that in mind. And if this, and what about the sum being a real number? What does that do for us?
Sum being real means I think they're either conjugates or opposites. Let me think. They
So-
either, oh wait, not necessarily actually.
Yeah, they wouldn't have to be conjugates. All we have to do for the sum is to cancel
Sum of
out
the
the
imaginary parts.
imaginary part.
Yeah.
Okay. So we have whatever Z1 is, the imaginary part. Z2, its imaginary part is going to have to be the opposite of that. So maybe if I drew a complex plane, and we have if Z1 ends up being on that line, then so that's Z1. Then Z2 is going to have to be down here. Okay. The real imaginary complex. All right. So we're basically trying to figure out how many possibilities there are. So we're kind of narrowing it down as we go along. Product is real, and we've got this sort of scenario happening. And then we find out that they're Gaussian integers. Real and imaginary parts of both are all integers. Absolute values, so they're Gaussian integers constrained within a square. And we got to figure out how many of these there are.
I believe if we wrote Z1 and Z2 as like A plus BI and like C minus BI, and we just manually expand, multiply them like that.
So you're saying Z1 is A plus BI, Z2, might as well, right? Z2 is A minus B, I'm sorry, not A minus BI. Maybe it's A minus BI,
Maybe.
but
Yeah.
let's call it C minus BI, right? Because for now, we at least know that the B's are going to cancel each other out. So
Right.
okay. So that's what we get from taking the fact that the sum has to be a real number, right? The BI, the plus BI cancels the minus BI. And we want the product of these to be a real number. So what does that give us?
Let's see.
AC plus B squared plus AC plus B squared
plus CB minus AB. Or
okay. So okay, and that product has to be real. So what do we know?
we know that C minus A quantity times B is 0.
Right. So either C minus A is 0, meaning that C equals A, and therefore Z1 and Z2 are conjugates. Or, wait, that's the only possibility, right? Because the other possibility would be that B has to be 0, which they've told us that these are non-real complex numbers in the first sentence.
In which case,
So we know that Z1 and Z2 are in fact conjugates, right?
Yep.
Okay. So this is a part of the problem where I like to go back and make sure that I've adhered to the constraints that we have and figure out where to go next, right? Z1 and Z2 are conjugates. Okay. Product of these, so we determined that has to be true. Is that sufficient, or do we have to go a step further? Right? So the product of these is a real number. We know the product of two conjugates is a real number. Their sum is also a real number. We know that the sum of two conjugates is a is going to be a real number. And the real and imaginary parts are all integers whose absolute values are less than or equal to 20. Okay. So it looks like we're just dealing with conjugate. By the way, if Z1 fits the bill, absolute, so that both the real and imaginary part has absolute value with less than or equal to 20. If Z1 fits the bill, then Z2 is going to as well, right? Because they're conjugates. So if one of them works, it's conjugate will. So we really just need to figure out how many possibilities there are for Z1. All right, how many do we have then?
Well, okay. How many integers whose absolute value is less than or equal to 20 would be minus 20 to 20 inclusive? All the integers in that range. So there are 41 options.
There's going to be 41 options for what? That's for the X value, right? Or for the A value and X value, the real part.
And then for B, I think it's also 40.
Except for one thing, right? We can't have the imaginary part being 0. So I think that
Oh,
one turns
right.
into a 40. Does that
That
sound
means
right?
it's 40, yes.
Okay, and 41 times 40 looks like we got 1600, and we got another 40. 1640, does that sound right?
I think so, yeah.
I like those complex number problems. All right, let's take a look at number 5. Okay, so we're expecting some sort of a quadratic here. It looks like, because of the form A equals root B over C. And then they're asking us to basically take that thing, the actual answer, and then turn it into effectively there's going to be a function that turns that into a 5-digit number. So okay, or possibly 6 or more digit number depending on how big it is. I think a lot of this is just drawing it out. You want to draw the diagram, Taiki?
Sure. So we have, it's gonna run 1 yard due north, and then runs some amount say that's the path, and then this is a 120 degree angle.
Okay.
All right.
So I think we're gonna. Can I mark this as a 2 then? Am I reading your diagram correctly?
Oh, right. Because they start 1 in this one. Yes. So if Emma starts, or Emma is here.
I got an idea. I
Yes.
think, because what's weird about this is we've got, I mean, this whole thing is parameterized, right? Like we have a time that we're going to hit each one of these locations. So you've got a location here, right? So you have this midpoint mark. So so I'm guessing you've got a 1 down here and a 1 here. Why don't you write the 1s in for the distance? I'll write, since I'm using a different color, this will be perfect, right? I'm going to write down what happens, where we are at various times. Right, so at time 0, we're right here. 5 yards per second. If I run 1 yard north, I am at 0.2 seconds. Okay, now you're drawing a 120 degree, roughly northeast. Okay, I see what you got when a bunny turns.
I think, oh.
So what do you think they mean when they say when a bunny turns?
I assumed it meant that the point where she moves northeast, starts running northeast.
Yeah,
But
we don't have any other information about some change that she's making, right? So, okay, so there's only one turn. We're gonna be turning this, basically turning 60 degrees clockwise to hit that new angle. Okay, so she wants northeastern line, new route, makes 120 degree angle. Okay, so when she turns, Emma throws the football 10 yards a second. Okay. at some point we're going to catch the football. So some point way out here, and we're going to have to do some calculation of this. Okay. So I think maybe the way I would start a calculation would be off of the distance, right? So maybe why don't you write an x for that length in your dashed line? Once you write an x for that, then then we've got everything else we need, right? Because I can then express the time, because if we're traveling an extra x yards, it looks like we're doing here. If I travel an extra x yards, then that's going to be x over 5 seconds plus the 0.2 that we had here. So we're talking x plus 1 over 5 as a time. If x plus 1 over 5 is the time, why aren't you drawing that other line? I'm getting a strong, yeah, I'm getting a law of cosines vibe about this.
Yeah. If we draw this 1 second,
Yeah.
then
okay,
since,
and
yeah,
we know that that distance, because the time, let's see, Emmett throws, when Avani turns, that means that we have Avani's traveling a distance of x, while Emma throws the football at 10 yards per second. So if Emma's traveling, if Avani is traveling x yards, Emma throws the football at 10 yards per second, then that means that the football is in the air x over 10 seconds. Is that right?
x over 10. Actually, it would be whatever this length is.
Oh, right. Yeah.
Actually, I think we can find this length by.
We don't even. So this 1 second here is irrelevant, right?
Pretty much.
So yeah, we don't even need that 1 second. What we need here is to say, okay, the amount of time that it's going to take to get to this point. Avani is running at a total of x yards, which means that the time it takes is x over 5. And then Emma is it Emma? Emma is going to be throwing the football, and we're going to take, and that's a distance of x, and so we divide that by 10 yards per second. So we're going to take whatever this is and divide it by 10, and then we'll be able to solve for x. All right, so I guess we just log cosines that then, right?
Yeah. Wait, actually, what I was thinking is like, so this run after turning has a distance of x. So then, since the football moves twice the speed of Avani's running, then
right,
and it takes
so
the same.
We just
amount
call
of
that
time.
2x at the bottom, and
Yeah.
then beautiful. Okay.
So I believe this distance would be 2x.
I like it. Yeah, then the whole time parameter is erased at that point, and we cut straight to the chase. All right, cool. So just to law of cosines it out really quickly, we've got what 4x squared equals. Talk me through this.
Or I think it's 4 plus x squared minus 2.
2 squared plus x squared minus
2 4x cosine. Which one?
Cosine 120. How much is cosine 120?
It's
Negative
minus
a half, right?
1/2. Yeah.
All right, so I flip the sign and I cut it in half. And so now we see, I'm going to pull this x squared over 3x squared. I'm going to pull over the 2x minus 2x, and then the 4 minus 4 equals 0. Check my work on that, Taiki. It's still integer coefficients and everything, so it shouldn't be too hard. We just work this out then. So what do we get? X is negative b. Plus or minus, we assume plus because otherwise it's probably going to end up being a negative distance. Square root of b squared is 4 minus a negative 4 times 3 times 4. That's going to be plus. Do I get 48 here? Does that look right?
All right. Yes. So root 52 is 2 root 13.
Okay.
So
Great. So a lot of it simplifies. We end up with what, 1 plus root 13 over 3. Okay. What does that give us for final answer then? Looks like we have to convert it using this
although
formula.
I think we still, well, that's the distance. So you have to convert it to second. Wait, so
Oh, right. So x was the distance. Good catch. No pun intended. What have we got? The time since Avani began running. That's where this 1 comes in. Okay. So it wasn't a red herring after all. It's a trap is what it is. Okay.
yeah.
So we know what x is, and the time is x over 5 plus 1. Okay. So my x plus 1 over 5 was relevant somewhere along the line. I thought it wasn't going to be until we figured out what they were asking at the very end. All right, so we got to do x plus 1 over 5. Plus 1 on this thing is going to give us, what is that, 4 plus root 13?
Yeah.
That's the plus 1 part. And then divide by 5 should give us a 15 on the bottom, if I'm not mistaken. All right, so what are we looking at? 400b is 1300, and then c is 15. Does that look right?
Yeah.
All right, let's keep going. So we're looking at the product of the elements of every subset.
Hmm.
And so what I'm looking at is the, I've got n elements. Each one of those n elements is going to show up a certain number of times in the product. Oh, no, the products are summed together. Ooh. Okay. I was thinking the products are producted together, which means we've got this big product.
I think I've, may or may not work, but I think you can write the product or the sum of the products as like 1 plus 1 times 1 plus 2 times 1 plus 3, etc. to 1 plus n. But that's because for each subset, you can choose to have the element in it or not have it in it.
Mm-hmm.
So I think that's the sum of the products.
Okay.
Yeah.
So you're saying that the sum of the products is going to be the product of from k equals 1 up to n, is it? Of 1 plus k?
Yeah.
Okay. Oh, that's gonna, I feel like that's gonna be problematic because this looks like a factorial, right?
Yeah.
As we start
Yeah.
with, because 1 plus k, I mean, that's basically just starting at 2, multiplying on up. So 2 times 3 times 4 all the way up. And then we've got, so that's a factorial of something. And that's not going to end in 99. No. Unless we're missing something. Maybe we're missing, maybe that thing you just described is, maybe it's offset by 1.
Can we describe this?
Because we could find, right, I mean, there's definitely a factorial that if we subtracted 1, then it'll end in 99 nines. Well, I say that, but I haven't verified it. But I mean, there's some numbers of zeros that you're not going to be able to end up. Okay. How about we? So we've got an interesting conjecture here, right? So maybe we test it out. Maybe we do this with with n equals 2. Right. So for n equals 2, let's non-empty subsets.
Oh,
there's a 1.
Subtract a 1 from.
So we are subtracting a 1 at the end. So this is our conjecture then, is this thing's going to end in 99 nines, and I need to find, let's see, if I multiply, so we can verify this a little bit later, but let's see if we can just zero in on a solution real quick. If I have my 1 plus k and we're taking that all the way up to n, that's basically n plus 1 factorial. Is that correct?
Yeah.
Oops. Minus 1 is going to equal something times 10 to the 99 minus 1. Does that sound right?
Yeah, as long as a is not contained.
Yeah, as long as we're a being a natural number, we're looking at so something times 10 to the 99 is going to give us 99 zeros at the end. And if we've got 99 zeros at the end, we subtract 1, we're going to get 99 nines. Okay, cool. So then we're just add 1 to both sides. Those minus 1s knock each other out. And basically we have n plus 1 factorial ends in 99 zeros. Okay. And we want the smallest one to test it. I think we got this. So
I think
ending in 99 zeros. I mean, I'm looking at probably about like 125 or something, right? Or am I way off on that? Oh yeah, I think I'm way low on that. So how are you going to get 99 zeros? Well, let's 80 or so zeros are going to come from just your multiples of 5, and then so if I say let's just say, for instance, 400 factorial, right? So how many zeros does 400 factorial hit it? I take 1 for every 5, that's 80. And then I take, and then I divide that by 5. Right? So 80 divided by 5 is 16. I divide that by 5 with no remainder, and that's a 3. Right there, that gives me 99 zeros, right? So 400 factorial ends in 99 zeros. Yeah, that 125 I was thinking, I was thinking a factor of 1.25. So in general, what I found is that, if you want to find out how many zeros a certain factorial ends in, it's about a fourth of the number. Right? So 400 turns out to be almost a fourth of 400. Turns out to be exactly 99, which means we need 1 more 0. So it looks like 405 factorial is going to be the thing that matches up with n plus 1 factorial, giving n as 404, if that worked.
400 factorial ends with 99 zeros. Wouldn't
did I do that right? I might have.
Wouldn't 400 then be the n plus 1 or wait? Or how come you want 405 instead?
Oh, what? Why was I looking for 405? I was thinking 100 zeros for some reason. Why was I thinking 100 zeros? We already had the 99. I was aiming for 100 because that was my estimate. Right. No, you're absolutely right. 99 zeros is exactly what we want. So if 400 has 99 zeros at the end of it, then that means n plus 1 has to be 400, and n is 399. Is that correct?
Yeah, I think so.
All right. Thanks for catching my mistake on that one. Yeah, 99 zeros is what we want to end up with. I just estimated 99 as 100 and forgot to make it exact in the end.
Oh,
Okay, so if your conjecture up here is correct, then everything else falls right into place. We've got this. So, talk to us again about why you've got this 1 plus k business.
because for each subset, for each product of that or for the product of that subset, we can have either the element in S be in the subset or not in the subset. And if it's not, then it counts as just 1 instead of k. So
this is it's basically like this is binomial theory, right? So we take x plus y to the nth power, right? And what's our coefficient? Well, it's going to be how many times can you choose an x versus how many times can you choose a y, right? So like if I have x plus y to the n, I'm basically multiplying x plus y n times, and then in each one I'm picking an x or a y. And so what you're saying is picking the y is effectively like taking that particular number into my product, and picking the x is like not taking, which is a 1. And so basically for every possibility of all of the others, you build it up inductively, right? If I have a bunch of stuff and then I add an extra number and I add an extra element into the set, then I'm going to take that number times all the other stuff. That's my k. And then I'm going to take it not using that number. I'm going to multiply all the other stuff, and that's the 1. Okay, that makes sense. And the correct answer is 399, by the way. So I love the approach up here. Now the -1, I think we conjectured that, right? Because we're like, into 99 nines, this is a factorial. If it's going to end in 99 nines, we've got to have a -1 somewhere. And I think that's where the non-empty subset thing came in, right? Because if you do multiply all these out, you're going to have a 1 times 1 times 1, which represents the empty subset, right? So you have that extra 1 hanging around. We've got to subtract that 1 for the empty set, and then we're off to our 99 zeros. Okay, now what I wrote over here was, I was basically going to set up the framework for let's test this out. N equals 2, N equals 3. And, I would recommend that anybody who's, not convinced about this product of 1 plus k's, that might be a way to go. Test it out with some small values so you can see it working, so you can see the, the kind of combinatorial nature of it and how it all gets joined up. But I think we can move on to the next one because we got the answer here, and it came up with a nice approach for it. So I like that. That's a cool observation on that product. All right, number 7. Product of the digits in base 3. All right. So it looks like we just do this whole thing in base 3. So 3 to the 7th minus 1. That's just going to be 7 2s in a row. Is that correct?
Yes.
There's n equals 1. 3 to the 7th minus 1 is 7 2s in a row. Feels a lot like the last problem. Product of the digits. So all we have to do is add up all of these and product of digits. I feel like we're going to want to do this digit by digit. Are we going to do that? We're going to want to split into cases based on the number of digits. Is that your impression, or do you see a shortcut to avoid casework?
I have a feeling there might be a similar shortcut, but this time I'm not sure.
All right. All right, let's casework. Let's start with the 7-digit numbers. Okay. So when we talk about the 7-digit numbers, basically anything. Okay, so I usually like to make a chart on these sorts of things, and I'm going to start with the hard one. So 7 digits and the sum of the products. So, okay, so 7-digit numbers. Here's what I'm looking at, right? 7-digit numbers are always going to start with a 2 or a 1. Anything that has a 0 is out because we're talking product of the digits, right? So the product is 0. So we're only looking at things that have nothing but 2s and 1s. Well, the 1s don't contribute anything. So the real question is how many 2s are there if I've got a total of 2s and 1s? Right, so as you can see here at the very bottom, I could have as many as 7 2s. That gives me 128. One of these could be a 1, but we have to. Ooh, we got a combinatoric system, right?
Yeah. All right.
There's
so
possibilities. Ooh. Okay. Now I'm worried about too much casework. So what's the trick?
And so you gave me a good idea, and that's that like if t of n is greater than 0, then the digits are only 1 or 2, 1s or 2s. So you can find how many numbers have.
Wait a minute, is this just 0 plus 1 plus 2 times 0 plus 1 plus 2?
Yeah, that's another way.
Okay,
I think so.
Combinatorially again, we can build up every one of these that way. So we're looking at, So we're going up to 3 to the 7th minus, starting at 1, going up to the 3 to the 7th minus 1. This whole thing is 3 to the 7th possibilities. Then if we do 0, 1, 2 times, then we actually end up with 3 to the 7th possibilities, which because 0 plus 1 plus 2 is 3, and we end up with 3 to the 7th as our answer also. So let me just write that down. So that's if we take all the possibilities of 0s, 1s, and 2s. We don't have the 0, right? The 7 zeros in a row. So, but because we're starting at n equals 1. So if we wanted to be complete and add all 3 to the 7th possibilities, we've got a 0 thrown in there. So I guess, we subtract 0 at the end. So the answer looks like it should be 3 to the 7th, but what is 3 to the 7th? 3 to the 6th is 729, and then I just multiply that by 3. 2187, as in FN 2187. Okay, that's not what they're telling us in the answer key. So we did something. We must have made some kind of an assumption here that we have to be careful.
Did the answer have something different?
Yeah, the answer key is telling me something else.
Oh. Oh, because in 0, 0, 0 to 0, 1, the product isn't 0, it's 1. So like
Oh,
it's, yeah, because you can't do 0, 1, 2 just because that assumes that the product with something starting with 0 is 0, but it's not 0.
ooh, okay. So very similar to the last question, only they threw in an extra trap on it. Okay, so is that going to make the final result bigger or smaller? Should make it bigger because we counted that
Bigger.
that 0, 0, 0, 1 as 0 when it's really a 1.
So
Well, hold on then. So this we just calculated. If what you're saying is true, we just calculated the answer not for everything, but only for the 7-digit numbers.
yeah,
Okay. Which means I need to add in the 6-digit numbers and the 5-digit numbers and so on all the way down.
yeah,
So in other words, I need to add 2187, which is 3 to the 7th, plus 729, 3 to the 6, 5, 4, 3, 2, 1, and 0. I need this number. That should be our answer, correct?
probably. I feel like the 3 to the 0, wait, does that count? Like, because if there's a 1-digit number, then 3 to the 1 would be, but the last digit is 3 to the 0. But so I think it's like 1, 1, 1, 1, 1, 1, then 0 or something. Or like 3 to the 0 doesn't count. Or what does it? I don't know how to explain it.
Okay, so there's 2187 of these that start with a a 1 or a 2. All right, so we've got 1 plus 2, which is 3 times 0, 1, 2, 0, all the way down. And those are all yeah, okay. So that should work. So 2187 for that, and then 729 for the 6-digit ones, 5, 4, 3, 2, 3 for the 1-digit ones. Oh, right. So there's going to be 7. We have 7, 6, 5, 4, 3, 2, 1 digits. So there should only be 7 ones here. But in order to get a 2187, it has to be in the 8th digit. So you're saying that number right there is a 0, right?
Yeah.
All right, cool. So so I want this thing. So that's my answer, in other words, which is wonderful. If I can just add this up. Now, I can add it up. I mean, you see, I started to do the beginnings of that over here, but no, I don't want to bother with that. What I want to do instead is say, okay, this is what I want. I'm going to call it X. And then I'm going to say 2x is equal to 2, 2, 2, 2, 2, 2, 2, 0. And then 2x plus 3 is going to give me 3 to the 8th. Right? If I add 3 onto that number that I had there, I'm gonna roll the clock over the odometer, whatever you want to call it, to 1, 0, 0, 0, 0, 0, 0, 3 to the 8th. And we know that 3 to the 8th is 65, 61. Subtract 3, we get 2x equals 65, 58, and x equals 3279. Got it. And that is the answer that they gave. Awesome. I like that. That was some teamwork there. Good stuff. Okay. Let's keep going. Number 8. Okay, so the log of k. And we just need the greatest integer of that. We need the last 3 digits. All right.
Let's see here. I think I would try to find the points of or values of k where the floor actually changes from some integer to the next one.
Mhm. So we're
Yeah.
10 to the 2019 is such an incomprehensibly large number that we figure that we're not actually going to, we're not even going to be adding that many things, even if we knew what the results were already. I'm assuming that vast portions of this are just going to be a waste anyway, right? They're just going to evaluate to 0, or they're going to evaluate to a multiple of 1,000. So, right. So 2, when I take the log of 2, I'm going to get something that's like a fraction. When I take the log of that fraction, I'm going to get a negative number.
Oh.
I'm going to pull up my calculator real quick. I'm going to test it out, right? Do I have a log button on my calculator? Seriously? Okay, here it is. Log of 2, 0.301. I knew that. I should have remembered. And then the log of 0.301 is negative 0.52. So for k equals 2, then the thing that I'm adding in is a negative 1. When does it stop being that, right? If I hit 3 and I take the log of 3 and the log of that, I get negative 0.32. I think it stops at 10, doesn't it? Because the log of 10 is 1 and then we get a 0. Okay, so from 2 through 9, I'm getting a negative 1 on this. And starting at log of 10 is 1, log of 1 is 0. I'm going to get a 0. And then, of course, at some point, we're going to switch over to 1. When does it switch to a 1?
That's when log base 10 of k is 10, right? So 10 to the 10, wait.
10 to the 10 is going to give us a 1?
I think so.
Because the log of 10 to the 10 is 10, and then the log of 10 is 1. Yep, so 10 to the 10 is the first 1 that we get.
And then we hit 2 when we have like 10 to the 100.
10 to the 100. And then we get 3 when we hit 10 to the 1,000, right?
Yeah.
Okay. And then it's just going to be 3s all the way up. Okay.
Yeah. So then we just have to do the other.
We have to figure out how many numbers we've got here, right? Yeah. So, all right. So 2 up to 9, that's 8 numbers times negative 1 is negative 8. So I got the negative 8 to work with. From 10 up to 10 to the 10th minus 1, I've got all those zeros. That's a 0 to work with. And then for the next one,
10.
We're just calculating the number. So you know, obviously the ones, they're going to start at 10 to the 10 and end at 10 to the 100th minus 1. But that's the same as starting at 10 to the 10 plus 1 and ending at 10 to the 100 if we're just enumerating them. And so to get that, we just subtract 10 to the 100 times 10 to the 10. And that's all ones. Then we do 10 to the 1,000 minus 10 to the 100, and that many 2s. And then we do 10, this one's the tricky one, 10 to the 2019 minus 10 to the 1,000. plus 1 times 3. Did I get that right?
Think so. Yeah. All right. So.
Okay, this is a multiple of 1,000. Agreed?
Mhm.
Okay, so that gets knocked out since we're dividing by 1,000. The 0 gets knocked out. So these get knocked out also, right? 10 to the 1,000 minus 10 to the 100. Both of those are multiples of 1,000.
Mhm.
Oh, yeah, I think a lot of this. Okay, 10 to the 2019 is a multiple of 1,000, 10,000. So those get knocked out, and we're left with a 1 times 3. So we have 1 times 3, which is 3, minus 8 is -5, which is congruent to 995.
Mhm.
Okay, looks good to me. I got to tell you, this -8 part, that was tricky. We caught it, which is good. So, all right. Yep, 995. That's what the answer key says. We are good to go. Let's keep going here. So this is square A. This is square B prime. We just need to find the ratio of the side lengths here, right? 80% of A is inside B. That means that 20% of it is outside. That means this is 5% right here, right? Each one of these little wedges is 5% of the whole thing.
Yeah. That means.
Oh, I think this is going to be pretty straight.
Yeah.
That means that this square here would be 10%. So we're looking for the square root of 0.1, and that's going to be this thing. So, so let's say that the side length of A is 1. So I'll put it like this: AX equals 1. Right? Well, maybe I should call this a Y. YX equals 1. Then I've got this point here, P, right? I'll say that YP is equal to the square root of 0.1. I'll just leave it like that for now. Is that right? YP is the square root of 0.1. That means when I take the square root of 0.1 times the square root of 0.1, I get 0.1. Cut that in half, I get 0.5. There's 0.5 here, 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 and here. That gives me 0.2 that's outside, leaving 80% of A inside. So now we've got a root 0.1. We've got a root 0.1. And then the rest of it is 1 minus 2 root 0.1. Well, this is all pretty straightforward then, because this right here is 1 minus 2 root 0.1 divided by root 2. This part is a root 0.1 times root 2. And we got this over here as well. So we have a side length, like it's all numbers at this point. I've got a side length for square B prime, which is 2 over root 2, which is root 2 times 1 minus 2 root 0.1, plus this piece down here, which is root 0.2. Yeah, this is it, right? Is it that straightforward? Root 2 minus 2 times root of 0.2 plus root of 0.2. That's minus root of 0.2. Is this all correct so far?
Maybe. Probably.
Let's see. So look at if I look at the format that they're asking us for, it looks like a difference of roots. So that's promising. Certainly. P, Q, R, S are positive integers. Okay, makes sense. Q and R square free. Okay. Let's keep going. Root 0.2, what am I going to do with that? That's the square root of 1/5. That means it's root 5 over 5. Root 2 is going to be 10 root 2 over 5. So that's what I'm getting. Does that fit the format? P is 10, Q is 2, R is 5, S is 5, 22.
Wouldn't it be 5 root 2? 5 root 2 over 5.
Where am I getting a 5 root 2 over 5?
Because like we had
Oh, this
root,
is just a root 2, wasn't it?
yeah.
Oh, okay. Yeah, so that was just a root 2, so that's 5 root 2. Okay. So now we got 5, 2, 5, and 5. So 5, 5, 5, and 2, 17 for an answer. Okay. Yes, I'm not sure how I took root 2 and multiplied it by 1 and got 10 root 2 over 5. That was good catch there. Okay. So and we do get 17 as an answer for that one, so that's looking good. An 11 by 11 grid with 9 by 9 squares and 1 by 2 dominoes. Okay, so my first thought is there are basically two things we can do with this 9 by 9. Right, we can put it in the middle, which is going to give us 2 tilings if it's in the middle. Correct? Just up to parity.
Probably, yeah.
Because if I've got a 9 by 9 in the middle, then I put it down. I put a 1 by 2 anywhere, and then the rest of the border is completely determined. But if I shift that 1 by 2 one space over, I get a completely new thing. But if I shift it over again, I'm back to the original one. So there's 2. So if I have this 9 by 9 in the middle, then I'm going to have two terms. But then if I have the 9 by 9 in the corner, then whatever I have from one of the corners, I'm going to multiply by 4, right? So I'm going to have 4 times something. Okay, so we just got to figure out, we've got to figure out the number of tilings for, what does that give us now?
I feel like it might be 0.
So
But
there's
I don't know.
2 by 9 and 2. That's not 9, it's 11.
Never mind. Yeah.
Let's take this point right down here at the bottom right. If it's up, then one next to it has to be up, and we complete a 2 by 2 square. If this thing goes to the side, the one above it has to go. The one above it does not have to go to the side. So we're not simply partitioning these things into squares. This is a Fibonacci field too. I've seen something like this before involving Fibonacci. Okay, let's focus up on the corner here because this is the weird thing, right? I've seen this sort of stuff before, right? You tile a 2 by n thing with 2 by 1 dominoes. I've seen it before. We could replicate it quickly. We could probably verify pretty quickly if it is a Fibonacci thing. That corner is a little weird though. I haven't seen something like that before, right? So without loss of generality, I can just say that this top domino is horizontal, whatever. What I can't do is I can't make this one vertical. Or can I? I can make that one vertical. What I can't do is I can't cross over like that.
Yeah.
Because now we're going to have a parity problem, right?
Mm-hmm.
Okay. So if I can't have that, then that means that I effectively seal off this section.
Yeah.
Right. So now I have a 2 by 9 section and a 2 by 11 section.
Yeah. You can make this a 2 by 10 section. I think.
Yeah, see, yeah, that's the thing. We've got, oh, right. So whichever one, if this is horizontal, then this turns into a 2x10, and this is a 2x9, and they're completely independent of each other. If, on the other hand, this one is vertical, then I've got a 2x9 down here and a 2x10 over here. Again, completely independent of each other. Okay. So there are two possible positions for this corner one. Horizontal gives me a 2x10 and a 2x9. Vertical gives me a 2x10 and a 2x9, but they're mirror images of each other. So this thing's going to be doubled. So my 4 times k, turns out that k is actually 2 times something, right? We'll call that a different k. I probably should call it p. Actually, what I'll do is I'll call it p. I call it p9 times p10, right? Where so basically I've got 2 arrangements of this thing, right? The two mirror images, right? Whatever you have, and then the flip along this diagonal. And whenever I have that, I'm then going to have, for each one of the 2x10 arrangements, I'm going to call that number p10. I'm going to have whatever we have here, the times the number of 2 to the 9 arrangements, or 2x9 arrangements. I'm going to call that p. Right. So what we need is a function, p. We need a function, p of n based on whatever n is. Okay. So, and I remember it's vaguely Fibonacci. Let's see what happens. So we know that p1, right? If we have a 2x1, that's a 1. P2 is, there's 2 arrangements, right? So 2. Look at that one. It's 2, P3. If I've got a 2x3, I can either start with a vertical, giving me 2 options, or I got 2 options here, giving me a vertical. I've double counted that. I double counted something. There's only 3 possibilities, right?
Yeah.
So I've got 2. If 2 of them are if they're all vertical, that's one thing. If anything is not vertical, that means I've got a pair of horizontals, and then I have 2 options with a vertical on either side. So that's a 3. And then P4.
Yeah. I think it's
P4, they could all be vertical. That's a 1. Let me write it out with this. 1 if they're all vertical. If I have 2 of them horizontal, then I have 2 horizontals. I'm sorry, I have a pair of horizontals together with 2 verticals. That's a 3 choose 2 situation. So that's a 3. I could have 2 horizontals, 2 pairs of horizontals, and that's a 1. 1 plus 3 plus 1 is going to give me a 5. P3 is the same way, right? I could have all verticals, which is a 1, or I could have a pair of horizontals, which gives me a 2. The 2 comes from the 2 choose.
So yeah, looks like Fibonacci.
So P5 is going to be a 1 if they're all vertical. If I have a pair that's horizontal, then I have 4 objects now. So that's 4 choose 1, so it's a 4. And if I have 2 pairs of horizontals, then I'm left with 1 vertical. That's a 3 choose 2 situation, which is a 3. 1 plus 4 plus 3, 8. Right? We do have Fibonacci numbers. That 2 up here, by the way, is 1 plus 1. And you can even see what's happening here, right? We've got so I mean, I haven't actually set this up as Fibonacci. I've set it up as something very different, right? I've got ones which are in choose 1. I'm sorry, in choose 0. I've got 1, 2, 3, 4, which is into 1. I've got 1, 3 something, and then that's going to end up being like into 2s. So at any rate, looks Fibonacci enough to me. And there is a nice inductive proof about this, that basically we're looking at P9 and P10. So P5 is 8. We could just, I mean, we're close enough. We can just push this on through. P6. I don't have to do the adding now that if you can believe that it's Fibonacci, we do it by induction. If you don't believe it, P8 is 34, P9 is 55, and P10 is 8. All right. So what do we got? 4 times 2 times 55 times 89.
Yeah.
Sounds a little computationally intensive, but okay, whatever. Let's do it. 55 times 2 is 110, so that's helpful. And then what am I left with? 4 times 89. Well, 4 times 90 is 360, so that's 356. So 3560 times 11 gives me 0, 6, 1, 9, 3, 39160. Plus these 2.
Oh, yeah.
Oh, that would have been crazy, right? You get that close to it and not get it. 39,162. All right, that's pretty cool. All right, so that's our team test for state for the high school state meet in 2022. Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.